Hello, and welcome to Module 3 of the INFORM Subnational training. In Module 3, we discuss designing, building, and maintaining the model. As a reminder, in Module 1, we discussed the vision and principles of the INFORM approach. Module 2 shared knowledge on how to manage the INFORM Subnational process. Remember, an INFORM Subnational Risk Index is much more than simply data. Buy-in, participation, and partnership are essential to the methodology. In this module, Module 3, we'll get more technical. This is where we take the data that partners share and combine it to build an INFORM Subnational Risk Index. We share the mindset, skills, and specific steps required to process raw data into a complete INFORM risk model. This includes an overview of the risk concept, the components of the model, and the tools and templates required to finish and share the model. We will complete this process using the exact tools and steps that you will use so that the process is clear and understandable. We will work with sample data to illustrate the full process from start to finish. Module 3 is divided into two parts. The first section describes the process and provides useful resources. The second section describes the 10-step technical process required to develop a subnational INFORM risk index. In the first part, we'll provide an overview of the technical process to have a top-line understanding, and then review key concepts and resources necessary for understanding and completing the technical process. As we move through this module, we need to remember the high-level process that we are following. While we provide many technical details along the way, this high-level process is simple. We are building a framework that describes the context, finding data, and combining this data into an index. We then review and adjust to make sure that the system works for our needs. As we introduced in Module 2, the development of a theoretical framework is the first step for completing the INFORM Risk Index. The theoretical framework provides the basis for the selection and combination of variables into a meaningful composite index. The INFORM Global Risk Index theoretical framework is a good starting point, but we must adapt some components to fit our local context. The INFORM Global Risk Index is based on risk concepts published in scientific literature. This literature defines three dimensions of disaster risk. These are hazard, exposure, and vulnerability. These are events that could occur and exposure to those events. Vulnerability is the susceptibility of communities to those hazards. The INFORM concept combines exposure and hazard and adds a third dimension showing the coping capacity or resources available that can alleviate the impact of the other dimensions. The INFORM risk model balances two major forces: the hazard and exposure dimension on one side, and the vulnerability and lack of coping capacity dimension on the other side. Hazard-dependent factors are treated in the hazard and exposure dimension, while hazard-independent factors are divided into two dimensions: the vulnerability dimension that considers the strength of individuals and households relative to a crisis situation, and the lack of coping capacity dimension that considers factors of institutional strength. The INFORM risk model adopts the three aspects of vulnerability reflected in the UN ISDR definition. The aspects of physical exposure and physical vulnerability are integrated into the hazard and exposure dimension. The aspect of fragility of the socioeconomic system becomes INFORM's vulnerability dimension, and the lack of resilience to cope and recover is treated under the lack of coping capacity dimension. The split of vulnerability into three components is particularly useful for tracking results of disaster reduction strategies over time. Disaster risk reduction activities are often localized and address particular community-level vulnerabilities and capacities. Please read the detailed INFORM methodology document on the informindex.org site for more information. The United Nations and relevant scientific literature express risk using the equation risk equals hazard times exposure times vulnerability. In order to accommodate the INFORM risk index methodology, where the vulnerability variable is split among three dimensions, the equation is updated to Risk equals hazard and exposure times vulnerability times lack of coping capacity. In this form, INFORM's score is more susceptible to vulnerability and lack of coping capacity. These are the forces of risk that can be most influenced by development and disaster risk reduction activities. The INFORM Risk Index includes the 3 dimensions of risk. The top row of the picture, hazard and exposure, vulnerability, and lack of coping capacity. Each dimension encompasses different categories. The second row of the picture. Finally, there are many components within each category. Dimensions and categories remain constant in all models, while the components within each category are tailored to the subnational context. They are carefully chosen based on partner consensus and available data during the consultation and workshop process. This approach means that the specific risk scores of each regional INFORM model cannot be specifically compared to the risk scores from another subnational model. So the regional INFORM model for the Sahel cannot be directly compared to the risk scores from the INFORM Lebanon model. The INFORM process does not include primary data collection. All data for the module must come from existing, open, reliable, and verifiable sources. The subnational model is only as strong as the secondary data that feeds the calculations. Subnational leads must determine if there is a critical mass of suitable data before initiating the process. Indicators are data sets that capture a specific topic, for example, exposure to floods or gender inequality. Partners choose indicators for each component. These indicators are the individual data sets that make up the INFORM risk model. They may include the number of people exposed to earthquakes of a certain magnitude, the number of displaced people, or food security indicators at the subnational level. Indicators may be composite indices in themselves. In all cases, indicators must be open source, continuous, provide full coverage, and they must be available at the local level. Indicator selection is usually a compromise between a data-driven and a user-driven model. There are always some components which existing data cannot describe, especially if the demands for quality of data are very high. Now let's examine the fixed dimensions of the model in detail. A solid understanding is essential for selecting the right components. Hazard and exposure. The INFORM index shows risk to people. The hazard and exposure dimension reflects the probability of human physical exposure associated with specific hazards. There is no risk if there is no physical exposure, no matter how severe the hazard event is. Therefore, the hazard and exposure dimensions are merged. This represents the load that the community has to deal with when exposed to a hazard event. The dimension comprises of 2 categories: natural hazards and human-induced hazards. These are aggregated with the geometric mean, where both indexes carry equal weight within the dimension. The diagram on your screen outlines the range of natural hazards and human-induced hazards. Feel free to pause the module to examine the diagram in detail. Vulnerability. The impact of disasters on people in terms of the number of people killed, injured, and made homeless is predominantly felt in lower-income countries, while the economic cost of disasters are concentrated in high-income countries. The vulnerability dimension addresses the intrinsic predisposition of an exposed population to be affected or to be susceptible to the damaging effects of a hazard. The assessment is made through hazard-independent indicators. So that means that the vulnerability dimension represents economic and political and social characteristics of the community that can be destabilized in case of a hazard event. Socioeconomic vulnerability and vulnerable groups are aggregated through the geometric average. Let's take a look at the range of vulnerability split between socioeconomic vulnerability and vulnerable groups. For the coping capacity dimension, the essential question is which issues the government has addressed to increase the resilience of society, and how successful has this process been? Specifically, we measure the ability of a country to cope with disasters in terms of formal, organized activities and country government efforts, as well as the infrastructure which contribute to the reduction of disaster risk. This dimension is aggregated by a geometric mean of two categories, institutional and infrastructure. The difference between the categories is in the stages of the disaster management cycle on which they focus. The institutional category covers the existence of disaster risk reduction programs, which address mostly mitigation and preparedness early warning phases, and the infrastructure category measures the capacity for emergency response and recovery. Please take a moment and review the lack of coping capacity diagram. Partners learning about the INFORM Risk Index for the first time often confuse risk and severity. Humanitarian organizations working on saving lives in a disaster often want to know the severity of the crisis. They want to know how many people have been affected by the disaster and what these people need to survive in the short term. Risk is the combination of the probability of an event and its negative consequences. Disaster risk is not just about the likelihood and severity of the hazard event, but also about exposure and vulnerability. Please remind humanitarian-focused colleagues that the INFORM Risk Index is not a crisis severity index. This is not simply look at the map and send your aid there. This is a holistic picture of risk that includes data over several years. However, if a crisis hit an area that was deemed high risk in the INFORM model, humanitarians could use this assessment as one input in their estimation of a disaster's severity. Given this difference, INFORM partners have been working to develop a global crisis severity index. Please go to the informindex.org website to view this global crisis severity index. Now let's review the tools that the project manager and subnational lead use to build and maintain the INFORM Subnational Risk Model. The first is the project management tool. This is a basic project management tool that you can adapt for your specific project phases and needs. Next is the INFORM Subnational Risk Index spreadsheet template. This is an empty Excel or Google Sheets template with the formula for normalization and aggregation already complete. Next is the data checklist. We use this spreadsheet to track partner input and data status. This is the workshop agenda template. This is an agenda and sessions for the workshop where subnational partners reach consensus on the components of the model. We also include sample workshop presentations. We also include a basic contact list template. And finally, a meeting list template. This is a simple tool for organizing pre- and post-workshop meetings to track delivery on data and other commitments. Please also review the following links and resources found at inform-index.org/subnational. These are the Global INFORM site, the INFORM user guide, the INFORM Subnational platform, the INFORM application form, and the full INFORM methodology document. We'll now review the technical process that the project manager and the technical lead use to complete each subnational model. This is the most complex part of the training. You may need to repeat certain sections. At an open workshop, the project manager, in partnership with the subnational lead and partners, reach a consensus on the specific components of risk. Hand-drawn inputs and discussion notes from the workshop are reviewed to build a conceptual model that is tailored to the context. Put all those inputs together into a picture, something like this. Here's an example of the first INFORM Sahel workshop in Dakar, Senegal. This was an exercise covering the whole Sahel region. Partners defined specific components of risk that mattered in the Sahel context. This slide shows the starting point of the global INFORM datasets. Partners then validated the boxes with no fill and blue fill, with the new components that partners proposed in yellow on the three bottom rows. The components and subcomponents roll up into the model. It's also important to review existing documents related to the area of study, such as risk, vulnerability, or single hazard assessments. They can be used as inspiration, benchmarking, and comparison during the development phase of the model. Step 2. Selecting and collecting secondary data. Exchanges during the open workshop should also provide an indication of the available indicators to be considered for the model. The theoretical framework that we discussed in Step 1 provides the basis for indicator selection. Remember, the indicators should be relevant. The justification is based on evidence or the existing literature. They should be representative and robust, that is, focused on the component to be described. They should be quantitative and measurable. They need to be reliable and open source. They also must be continuous, consistent with coverage in the full area of your subnational model. Indicators have to measure the component's underlying concept. In most cases, a single indicator that can be used to describe the component does not exist. Relevant indicators that can then answer the question need to be found. Most of the time, strength in one indicator compensates for weakness in another. Step 2.1. Ensure and create admin code correspondence. The technical lead matches and in some case creates unique administrative codes to ensure that all datasets are comparable. Where possible, use admin codes that exist, such as P codes, in the United Nations system. The technical lead copies the identified admin codes together with the names of the units into the INFORM Excel template. Now let's start working with sample data. Open the sample data number 1. Also open the INFORM template. Select the P code data and copy it from the sample into the INFORM template. Paste the data into columns A and B of the indicator tab. You can now see that the data appears in the template. It also appears on the other tabs in the spreadsheet automatically. Step 2.2. Clean and validate. Clean, validate, and check the source of the data to ensure integrity and completeness. As we bring data into the model, we will find data sources that do not have P codes. We use the VLOOKUP function to quickly match the data to P codes and to bring the data into our INFORM Risk Index template. First, add a new column next to the name. Next, apply the VLOOKUP formula. As a search key, we use the name of the province. Next, go to the admin column and select both fields. This is an example, but you will be doing this in the INFORM template. Indicate column 2 as the search index. Then we indicate false to preserve correct and consistent matching. We then add the dollar symbol to keep the range fixed. We can then drag down the formula to all fields. Most provinces will have an exact match. If there is a spelling difference, you will need to go back and manually add the P code. Data treatment. Before we put the data into the model, we sometimes need to pre-process the raw data. This may include imputing missing values, adjusting into non-dimensional scales, transformation, and outlier identification. Imputing missing values. If data for some units are not available for a given year, we can impute the missing values using the data from the most recent year available. See the first example below. Other imputation methods such as interpolation, regression, or more advanced statistical methods can be used to impute missing values. At the end of the imputation, the missing values for each of the raw indicators should be less than 10% of the total values. Keep in mind that in a composite indicator exercise, it is not necessary to impute the missing values for every indicator, since the methodology can handle some data gaps. In the case of missing data due to weak coverage, the approach is to introduce more than one indicator for the same component to complement each other. See the second example below. The goal is to have a value for each component of the model. At the end of the imputation process, copy the data into the INFORM template. After the cleaning and imputation, we will now see an example of how to move the data from your working spreadsheet into your INFORM template. This is a simple process of moving the data by cutting and pasting into the correct locations in the INFORM template. The first step is to move the indicator names dimension by dimension from the sheet into the template. First, let's check the number of indicators that we have for hazard and exposure. It is 10 in this case. Now we go to the INFORM Index template in the Indicator tab and check how many spaces are available in the template. In this case, there are 10 spaces available. In this case, we can go back and copy the indicator names and move to the template and simply paste in the names. Next, let's move the indicators from our working sheet into the template for vulnerability. You can see that there are 18 spaces available and 26 indicators. We need more space in the template, so we simply insert columns to match our needs. Select the boxes on the left and drag them across the right to recreate the formatting and formulas. Next, we copy the indicators from the original file and move them into the template. Make sure to do the same for all parts of the data that you are inputting. Now we can go and simply move all the data from our centralized location into the template. Remember that you can do this in a batch, or you could do it one by one from various sources, depending on your configuration. Now all the data appears in the template. A quick note on adjustments to non-dimensional scales that we will use later in the process. In order to increase comparability across units, we should avoid absolute numbers where possible, and show how these numbers relate back to people. We can do this at the level of the selection of indicators, for example using GDP per capita instead of total GDP, or later with data processing, that is, dividing the number of people affected by natural disasters for each unit by the total population involved. Let's discuss transformations. Transformations are applied when raw data are far from the normal distribution. A log transformation is used to reduce the positive skewness of data, while the exponential transformation is used to reduce the negative skewness of data. A simple way to check if the indicator needs to be transformed is to create a bar chart with the ordered data and look at the distribution. If the curve formed by the bars is lower than the line, apply a concave down functional form, that is log or nth root. If it is higher, a concave up form, that is exponential or power. Let's now do an example of transforming data before it is normalized into the 0 to 10 INFORM score. Let's use the example of the physical exposure to floods indicator. We will do this by using a basic data distribution chart in the Hazard Distribution Indicator tab. We select the data from that indicator, copy, and paste. After pasting the data, we need to reorder the data to see the curve. Sort from highest to lowest. We can now see the data's distribution along a line. Ideally, we want normal distribution along the line. In this case, we have a concave distribution in relation to the line. In this case, we will apply a log transformation to bring the data close to a normal distribution. Apply a log formula to the first cell. Then select and apply to all cells. Now, we add the new transformation into the chart to check the distribution. Simply change the input column from A to B. We can now see our new distribution. Next, reposition your line to the new normalization. We have now normalized the distribution and can move on to the next step. Remember, this is not required for every indicator. Only use this process when necessary. Identify outliers. An outlier is a data point that is distinctly separate from the rest of the data. There are many techniques to identify outliers. We will use a combination of the following three items: existing standard limit values, skewness and kurtosis, and looking at data distribution and setting min-max. Let's talk about all three and then we'll go to some videos. For existing standard limit values, we investigate if there are recognized standards on how to interpret each dataset. For instance, if the indicator is used in other contexts by national institutions or international frameworks, then the interpretation is clear. For skewness and kurtosis, we want to check the min-max values for which skewness is lower than 2 and kurtosis is lower than 3.5. We do this using predefined formulas in the template. And finally, we look at the data distribution and set min-max. We sort the data, create a bar chart, and then check if the bars are distributed along a line. And then we use intercepts of this line to identify cutoff values, setting min and max. Let's look at an example of how to use the skew and kurtosis formulas already entered into the INFORM template. This is a way to check the distribution and look for outliers. The orange highlights show us where skewness is greater than 2 and kurtosis is greater than 3.5. Again, orange highlights indicate likely outliers. These will be the priority places to check for potential outliers. Check indicator by indicator to try to find the outlier. Let's take the example of the exposure to EVD indicator. We can see that the skewness and kurtosis scores are out of range. When we look at the data, we find that there are many zeros, which is an acceptable and normal part of that data. Whereas, perhaps with another data set, we could find an outlier that we could eliminate to have a more true understanding and interpretation of the data set within the model. Another way to identify outliers is to use the distribution chart that we saw in an earlier example. Using the monetary poverty data, we select the data and move it to the distribution chart. Again, we sort the data from largest to smallest. Take a look at the data distribution. Setting a min-max from the highest to the lowest would yield an undesirable distribution. However, if we move the line up, we could eliminate the outlier. We can see that the smallest value is definitely out of the main range. Identify the highest value, in this case 85, and identify the lowest value, in this case 40. This is your min-max. Make a note of the min-max values so you can transfer it into the template later. In step 4, normalization brings indicators into a common scale, which makes the indicators comparable. This involves making directional adjustments so the higher values correspond to worse performance on all indicators, and selecting a suitable normalization method, that is, min-max and thresholds, according to the conceptual framework and the data properties. We need to process and interpret each dataset to ensure comparability. We process the datasets into a scale from 0, lowest risk, to 10, highest risk, for each dataset in each region and subregion of the model. The normalization process aims to get a normal distribution of the normalized indicators, with 10 as maximum and 0 as minimum, and both the median and the mean of 5. The INFORM process uses the min-max linear normalization method, with some exceptions related to the nature of the indicators. As outliers often cause min and max values to be very different from the bulk of the values in the dataset, rescaling with a predefined min-max is essential. The choice of trimming the so-called tails of the indicators is supported by the need to avoid having extreme values that overly dominate the results. The minimum and maximum data point of the remaining dataset after the exclusion of the outliers are taken as the min and max. We prefer the min-max values to preserve the rescaling factor and make the transformation stable throughout the time series. We also exclude the distortion effects of outliers on the indicator set. We want to always consider the nature of the topic and try to reflect reasonable min and max values. Before normalizing the data, open the template and go to the Framework tab. Take a moment to familiarize yourself with the format. The framework shows all the data relationships and processing. We will now see an example of adding an indicator to the framework. Scroll down to the indicator level of the framework. We will now demonstrate adding a new indicator to the framework. The framework is here to give an overall picture of the processing, and it is not linked by formula to any other part of the model. Let's use the example of the monetary poverty indicator. We enter the indicator and talk about the type of normalization that we used. In this case, we use the standard min-max normalization. This indicator happens to match the INFORM approach, where a higher value shows greater risk. No additional redistribution is required. Let's look back at the chart where we normalized the min-max. There was no transformation required, and we already identified the min-max. Add the min-max to the framework. Let's insert the next indicator in the framework. Non-monetary poverty. We paste in the indicator name. And add the other information. Refer back to the distribution chart and add the min-max to the framework. Now let's move this into the vulnerability tab. We copy the indicator. And add the min-max. This transforms the data. Be sure to check the formula and make sure that it points back to the correct place in the indicator data tab. In this case, it is column M. After checking validity, You can replicate a formula from one column to another, like this. Simply copy and paste the formula across, and drag down the formula to all cells. Refer back to your framework and check the min-max. And copy the indicator name across. Add the min-max. After copying the min-max, watch the data transform. Now complete this process for all indicators in the model. Step 5. Aggregation. There are many different ways to aggregate the model. The one we choose depends on the methodology, which defines how the information from indicators should contribute to the overall composite index. There are several possible rules listed below: minimum, maximum, arithmetic average, and geometric average. The INFORM Risk Index methodology implements the arithmetic and inverted geometric average. Aggregation rules are applied to indexes at each level in order to progress through the levels in a hierarchical bottom-up way. That is, starting at component level and going up one by one through the category level to the dimension level. The dimensions are calculated by the geometric mean of the respective categories. The final score of the INFORM Risk Index is calculated with the risk index equation that we saw before. In arithmetic and geometric aggregations, weighting can be applied to control the contribution of each indicator to the overall composite, and this should be justified by the theoretical framework. Practically speaking, weights express a desired trade-off between indicators. This table shows an example of the differences between the two methods, with the arithmetic mean aggregating two similar scores, here from Ethiopia, or two very different ones from Nigeria, gives us the same result, while the inverted geometric mean, the latter, got a higher result towards the higher score. Arithmetic and geometric mean methods are applied according to their characteristics. Arithmetic means allow for perfect substitutability. This means that it is possible to offset a low performance in one dimension with a good performance in another dimension. The inverted geometric mean allows partial substitutability. This means that the more you have of one dimension, the more it will contribute to risk from that component. We use the arithmetic mean if we want to aggregate dimensions with similar properties, when the full compensation is welcome. So for example, internet users and mobile subscriptions are both indicators that describe access to technology infrastructure. We use the geometric mean when we need to compare dimensions with very different properties, such as earthquake, flood, tropical cyclone, and other natural hazards. They all are natural hazards, but they have very different characteristics. In general, the arithmetic mean is used for aggregating the base indicators and the lower levels of the model, while the geometric mean is applied to the higher levels of the model. Now let's go to a practical example of aggregation. You have all of your indicators entered into the template, into the framework, and you've done the normalization. The process of calculating a component of the model. Now we move up to the component. Here we fill out the framework to show how the components are aggregated together into the index according to the theoretical framework. We can scroll down to our example of the monetary and non-monetary poverty, and we can see they are put together into component 6. In our example, indicator 6 is economic growth according to our conceptual framework. And the aggregation method is arithmetic. Now we go back to the vulnerability tab to check the relationships. As we can see, we've already entered and normalized the data for these components. Now we need to roll these up into the dimension of economic growth. Now let's go to the formula. The formula is written so it still works if there is no data. And then we go to the average. Next, we make sure that all columns are added, so we add column E. Now we have an arithmetic average of the first 3 columns. Now let's do another example applying the inverted geometric average. Let's use the physical exposure to epidemic as our example. We used an inverted geometric mean to ensure that a higher value means higher risk. We see that these 4 indicators are a part of the same upper level dimension. We then move to the Hazard and Exposure tab, and we can see that the components are already entered next to each other. Let's put these together into a geometric mean. In the template, we see our inverted geometric mean formula. We add the component name, physical exposure to epidemic. Now let's look at the formula. In the template, it's aggregating only the first 2 columns. Here is the inverted geometric mean formula that we showed before. Watch the process on the screen as we copy the formula and add the other columns into the equation. Select and copy. Add a comma and insert. Then copy, then another comma. Next, change the column values. Now the geometric mean is applied to column G, H, I, and J. Always remember to drag down to all cells. After completing this process systematically, your model is ready. All parts from indicator to category to dimension are complete. Now, all the results should automatically appear in the main summary sheet. This includes the final risk value for every location in your model. Okay, time to celebrate, and also time to go back and check your work. Let's talk for a moment about how to troubleshoot any discrepancies that you have between the data that you've entered and the final summary framework. Systematically review and add the components that we calculated in the other sheets into the summary page. Let's go to our Hazard and Exposure tab, column K, and copy the name and bring it into the summary page. Paste in the name and make sure that the formula links to the correct place in the hazard and exposure page. Now let's go to the Vulnerability tab. Copy the name in column F. And move it into the summary page. Again, check the formulas to make sure they correspond. If you need more space, simply add more columns and make sure that the formulas correspond. In the completed model, all components are present and the calculation sheets are correct. Step 6. Interpreting the risk index scores. The INFORM risk index is scored between 0 and 10. The low values of the index represent a positive performance, and the high values of the index represent a negative performance in terms of managing the risk. The notion that higher is worse is consistently applied across dimension, category, and component level. For a better perception of risk, the units are categorized into different clusters based on their score and scores. As a part of your process, apply classes to each of the risk thresholds. That includes risk dimensions and categories. The classes should be used in all the communication material and in the maps. Use an R script to help perform the cluster analysis that is provided as a part of the training material. Go to the R website and download the software for your operating system. Open the software and load the data that you saved in your workspace. Open the script and select the cluster analysis script. Install the packages and load the libraries. Point to your working directory where you stored all the data. Prepare a CSV database of the INFORM results. Customize it according to your data. In the first column goes the name of the unit, in the second column the name of the ID. For the other columns, copy and paste the results from the summary page of the INFORM template. Add an X for no value. Run a selection and add the source. Run the script based on the ID. Move down and finally apply the cluster analysis. Make the calculation and show the results. We now have a cluster calculation in 5 categories, and you can review the distribution. Calculate this systematically for all the risk and dimensions across the model. To do this, we change the reference to the column in the CSV. Use a lookup table to assess the name of each different column and change the value accordingly. Run the script again with the new reference and record the results. Step 7. Validation. Once we complete the first version of the model, use a cross-correlation matrix to retrieve useful information on your model. Check the significance level of the correlation coefficients and the sign of the correlation coefficients. Avoid negative correlations. Avoid weak correlations. Avoid strong correlations. And check the balancing within the index. After you complete the model, release it first to a smaller core group of partners. After any updates, release it to the full partner group and update the model again based on feedback. Publish the model on the inform-index.org/subnational webpage. To maintain the INFORM model over time, decide on an update frequency, usually 6 or 12 months. Then follow the process that we described above, replacing older data with new data as it arrives and recalculating the scores. Thank you for participating in Module 3 of the INFORM Subnational Risk Index training. In Module 3, we got technical. We shared the specific steps required to process raw data into a complete INFORM model. This included an overview of risk, the components of the model, and the tools and templates required to finish and share the model. Our next module, Module 4, discusses how to promote and communicate about the model. Just doing good work is not enough. INFORM partners need to advocate with the humanitarian, development, and governmental communities to demonstrate the benefits of the model and ensure that all partners understand the process and opportunity that INFORM provides.